I'm just going to say for this next section that we're now going to be stepping away from the legal perspective and looking more at our local resources. And we have 4 speakers for this session. I'm going to ask them to come to the front so that we can quickly move between the speakers. And the purpose of this section is really to take a look more at what our local resources are, what do we have, how does it move through our system, how do we use them, fisheries needs, and where the science becomes involved in this and the importance of it. So for that, we have 4, as I mentioned, 4 speakers, and we're going to start with Jay Chenault. He is with Associated Earth Sciences. Some of you may have heard him talk about, he was actually involved in establishing our Instream flows back in the 80s. So he's familiar with our basin, and he brings, again, like many of us, decades of time spent working on these issues in a variety of places throughout Western Washington and beyond in many cases. And Jay's going to talk about an overview of where our water is, when it's available, sort of water budget things. And with that, I'd welcome Jay to the...
Thank you. As Sue mentioned, I'm Jay Chenault. I'm an associate hydrogeologist with Associated Earth Sciences. One slight clarification, I did do a presentation earlier this fall on the Instream flow rule. I was not involved in creating the Instream flow rule. But at any rate, I'm happy to be here to talk about this kind of very important overarching question, where is the water here in Whatcom County? And as you might realize, it's a very complicated and nuanced question, but it's pretty well captured by this photo. It's in here somewhere. It's both above and below ground, everywhere from the top of Mount Baker all the way to Puget Sound. And that the process of how water moves from Mount Baker to Puget Sound is generally talked about when we talk about the water cycle. So this is a pretty good diagram that's been around for a while in various forms from the U.S. Geological Survey. And it's essentially the cycle of how water moves through the natural systems here on Earth. About 97% of the Earth's water is out here in the oceans, and another 2% of the Earth's water is tied up for now, in the polar ice caps. So about 1% of the water on Earth is someplace in the rest of this cycle. So the cycle generally begins as evaporation into the atmosphere, either from the oceans or from other places on the land surface. And then as precipitation falls on the land, it can take many simple or complicated paths, either back to the ocean or back up into the atmosphere. And so the water is in here someplace. 1% of the water on Earth is someplace, in here, potentially available for humans to use. So when we start to talk about quantifying various elements of the water cycle, we generally start talking about it in terms of a water budget. So we move away from this nice cartoon of the natural system into more of a schematic diagram about putting water that starts as, in the atmosphere, and how we quantify various parts of the water cycle into these, boxes of this flow chart. So the water budget is typically expressed by this equation where precipitation falls wherever it falls. And then that participation is partitioned out into various components of surface runoff, both overland flow or as interflow, which is typically referred to the very shallow, unsaturated subsurface. Those two things, whether it's actually, you can physically see it flowing on top of the land surface or it's in the very shallow soils, typically referred to as a runoff component. And then you have both evaporation off of water surfaces and transpiration of plants. That is collectively termed evapotranspiration. That brings water back out into the atmosphere. Water that percolates through this unsaturated vadose zone into the zone of saturation or an aquifer is referred to as groundwater recharge. And groundwater recharge can be both to the shallow groundwater system or also in deep gravity drainage down to deeper aquifer systems. And so as you can imagine, as you get into this part of the water budget, a lot of these elements can move both ways. You know, water from the groundwater system can contribute base flow to streams. Streams can lose water to groundwater. And the same thing for deeper aquifers. You can move from one down to the other, and you can have upward groundwater flow from deeper aquifers to shallow. And there's also, you know, subsea outflow from any of these aquifers directly to saltwater. So there's lots of paths that this water can take through the water budget. So speaking of groundwater flow, it gets even more complicated when you get into situations with multiple aquifers as we have here in western Whatcom County. So aquifers generally, the flow in them moves from recharge areas or areas of high hydraulic head to discharge areas, either streams or other depressions, salt water. And the time that it takes for groundwater to move through an aquifer to those discharge areas can be highly variable. You know, it could be a matter of days, and shallow permeable aquifer systems from an area of recharge near the stream to the stream, it could move to weeks, months, or years as you move farther from that discharge area. And then it can get really long as you move through low permeability confining layers that separate different aquifers. You know, travel times can go from years to decades to centuries and even millennia as you move this long and tortuous path. This water flows through permeable zones and down through low permeability layers into these deeper confined aquifers, and either back up into discharge areas or out to subsurface flow. So I wanted to touch on, in terms of, you know, Whatcom County, a few large big picture projects that have been ongoing for several years in coordination with the Wire One Joint Board. The first one was called the Lower Nooksack Water Budget. The first documents came out on that in 2012, but I know work is continuing to be done in this area by this group of consultants. And so in that the project, they utilized a hydraulic model called TopNet, which is shown schematically here, and it's reminiscent of the relatively simple by comparison water budget flowchart I had earlier. But it starts with precipitation as the input, as well as other climate parameters, and it's a physically based mathematical model that calculates all these terms of the water budget. You know, is rain, is precipitation falling as snow or rain, how it gets intercepted by vegetation, how it flows through the shallow soil into groundwater zones, where it goes from there into channel flow, how much runoff is created, and then how does various water management elements fit in to both the surface water system, the vadose zone, and the groundwater system. So, you know, water management elements including irrigation, you know, withdrawals for other water uses, and then return flows as unconsumed water migrates its way back into the system. So it's a highly comprehensive model that was developed and is being utilized in the Lower Nooksack in particular. So, you know, the results of the model, you know, the primary input is precipitation, which can be widely variable, as you know, from across the county. About 40 inches per year here in Bellingham, over 200 inches per year precipitation up by Mount Baker. And so the results of the model is essentially a monthly quantification of all the water balance elements for many of the tributary streams in the Lower Nooksack Basin. And so this example is from Bertrand Creek, and as you can see in the Bertrand Creek area, you have relatively low precipitation, about 40 or 50 inches per year. And particularly in the summertime, the precipitation, you know, shown in purple is quite low, and stream flows are quite low. Evapotranspiration goes up, and so you have relatively low stream flows in the summer, and that is, of course, the time that water use is the highest. So the next project I wanted to touch on was the development of a conceptual groundwater model that a group of consultants led by AESI is currently working on. The main focus of the development of the conceptual model is to define the nature and extent of all aquifers and confining units that are beneath western Whatcom County. So where are the aquifers? Where's the water? Where are the confining units that separate aquifers? And how does that water move through those components? And it's really the first step in developing a numerical groundwater flow model of the area to actually start quantifying and simulating the effects of different actions would have on between the groundwater systems. So where is the water? Obviously, water in Whatcom County falls into two main buckets. It's either surface water or groundwater. The most recent water use work done by the U.S. Geological Survey partitions current water use in the county about 60-40 between surface water sources and groundwater sources. Obviously, surface water sources include the Nooksack River and its tributaries, also the Sumas River and its tributaries, and Lake Whatcom and other small tributaries that drain directly to Puget Sound. As was touched on earlier, surface water in Washington State was regulated by the Surface Water Code developed in 1917, and then the Nooksack River Instream Protection Program, which was adopted in 1985 as the big overarching theme right now that is regulating surface water use in the Nooksack Basin. In terms of groundwater, groundwater is available in aquifers. There's three principal aquifers, or four principal aquifers beneath western Whatcom County, which I'll touch on. Groundwater is regulated by the Groundwater Code of 1945. And then, as we talked about earlier with some of the other speakers, these Supreme Court decisions are essentially, the simplest way that I put it is they kind of link groundwater use to the in-stream flow rule. So where is the surface water? This is a color-coded map of the Nooksack Basin where in-stream flows or seasonal or year-round closures have been adopted as part of WAC 173.501. The areas in green, which includes the main stem of the Nooksack River and the middle fork of the Nooksack River, have in-stream flow rules established. The areas in purple may have in-stream flow rules established also, but are another level of regulation on those streams is that they're closed for part of the year. So no matter what the flow is in certain times of year, water is not available for out-of-stream use during those seasons. And then the areas in red are year-round closures exist on those streams. So some, like Birchen Creek, has a year-round closure, has in-stream flow rule also established, but it's administratively closed at the same time. So what you'll notice is most of western Whatcom County has some sort of regulation on surface waters. There's a few exceptions on these small tributary areas that drain directly to Puget Sound, and then some of these mountain watersheds that drain north of Canada don't have in-stream flow rules. So speaking of Ferndale, that gauge that was brought up earlier, so in the reaches and tributaries in the Nooksack Basin that have in-stream flow rules established that aren't either seasonally or closed year-round, water is technically available from these streams whenever the in-stream flow is met. So this is an example of 2006 river flow at Nooksack River at stream flow, or Nooksack River at Ferndale. So water is technically available for out-of-stream use whenever the flow is above this gray dashed line. So you can see there's periods here in January, then again in May, and then in November and December in 2006, where water would technically be available. So the problem is that although these periods where the stream flow will be above the in-stream flow are somewhat predictable, they vary quite a bit from year to year. And of course, the time of year when the in-stream flow is most likely to not be met is this low flow period between July and October, where water demands are typically the highest. And so this slide shows some predicted stream flows for that same time period, 2006, based on some climate change models that have been developed both by, this is University of Washington, but Western Washington University is working on it as well. But as you can see, as you move through time between 2006 all the way out to projected climate in 2080, this low flow period is getting longer. The flows are getting more extreme on the low end, and then these peak flows in the winter season are actually getting higher, as predicted by those climate models. So moving to groundwater, our project in developing the conceptual groundwater model for the county, we've identified 4 principal aquifers beneath Western Whatcom County. 69% of the wells in the database we developed are utilizing the Sumas aquifer, which is widely present beneath most of the western part of the county, and to a lesser extent this other surficial aquifer called the Everson Sumas aquifer, and then there's some deeper confined aquifers also present. So here's a map of the Sumas aquifer in light purple. As you can see, it's widely extensive across most of the Sumas and lower Nooksack Basin. The Everson Sumas aquifer is also present at the land surface here east of Blaine and then west of Ferndale. This is a hydrostratigraphic cross-section showing the deeper aquifers beneath the county. This kind of intermediate aquifer is we refer to as the Vashon Olympia aquifer. I think about 17% of the wells in our database are completed in this aquifer, and most of those areas are areas in the uplands, kind of around Ferndale, and some of the higher elevation areas that the Sumas aquifer is not present, and so wells are drilled into this Vashon Olympia aquifer. And beneath that, there's about 5% of the wells in our database are completed in this deeper Possession Whidbey aquifer. There's a few dozen wells that are in the county that are completed in this aquifer. As you can imagine, it's much more uncertain than these aquifers that we know more about. There's fewer wells. They're expensive and time-consuming to drill to, so it's more uncertain on that one. So to summarize, where is the water? In the surface water, in-stream flows and closures effectively eliminate new uninterruptible water rights, surface water rights in Whatcom County. There are interruptible water rights that are technically available, but because of the timing issue of when water is available and when it's mostly needed, it requires some creativity or some significant storage to be able to use that water when it's needed. And then, of course, you got to mitigate for any potential impairment. And groundwater, these unconfined shallow aquifers, particularly the Sumas aquifer, generally have a high degree of continuity with surface water. So they're kind of lumped into this same category as what regulates the surface waters. Deeper aquifers generally have less continuity with surface water, but then this catch-all is, there's still any potential impairment to in-stream flows or other senior water rights needs to be mitigated for. So I think that's it.
Okay.
All right, thank you.
The next section we're going to be talking about, which is me actually, and this is kind of interesting because I usually only moderate these, and now this is a chance to actually do one of the sessions. We wanted to make sure as a planning committee that we included information on who's using the water, and even though my role as extension doesn't involve doing these estimates anymore, I have been involved for decades in various groups and consulting firms and local efforts to estimate water use, and so I said, sure, I'll do it. And it wasn't as easy an exercise as I thought it was, had hoped it would be for this, but it's very interesting. The information is really useful. And so here's the categories that we're talking about once again. We've got public water supplies for the purposes of this discussion, and these are actually the categories that USGS uses in some of their water use estimates. That is, these are systems that are basically 15 connections, 25 services, and larger. So we have a lot of those in the county. You're going to see about that. Domestic are the smaller ones, and all of the individual wells are people that are getting their water from surface waters. Irrigation is pretty self-explanatory, as well as all of the other categories there. And for this exercise, I really didn't want to just paint a snapshot of, okay, how do we use water? Where is it coming from at this particular point in time? Because when we're really, as a community, talking about how do we deal with our water issues now, it isn't just a point in time. It's looking at what are our issues now? Where do we think we need to be with this stuff? So understanding sort of the past into the future to the extent we can is really helpful in mapping out our solutions. So to the extent that I was able to, I would be providing you with some of that information. And the good news and the bad news is we have a lot of sources of information that you can go to with this, and trying to make sure we're collecting and using the stuff that's the most accurate and valuable and gives us the level of detail that we want can be a challenge. Here is just a list of some of the major sources that I used in this presentation. USGS, the YR1 project has got a lot of the studies and reports that are going to be referenced here. Whatcom County recently did a coordinated water system plan. That's referenced. Washington State Department of Health has got some really great information. If you are interested in a particular water system, they've got a website that you can go to look very specifically at those systems, and USDA is really a valuable source for agricultural information, as well as many other things like individual water system plans. I am including links in this presentation. The PowerPoint will go up. So if you want to take a look at any of this stuff in more detail, this is an easy way to get to it. And there is a ton more information on these sites than what I'm going to cover here today. I am staying pretty 40,000 foot level, broad relationships. What the heck do we have a basketball court there for? Well, there's a reason for that, because the data that I'm going to have you look at, that I'm reporting in, is mostly in million gallons a day. How big is a million gallons a day? I mean, getting that sort of a concept of that, USGS says it's 51 feet by about 51 feet by about 51 feet. Well, that still doesn't really cut it for me. So not that I am a big basketball fan, but sports, we have to have something related to sports. So the person that helped me put this together said, well, let's use a basketball court. So that's how much a million gallons looks like, about. Another way of looking at it, and this is particularly useful when you consider that we just saw information on how much water we get in this county, which is anywhere from 40-some inches up to over 150. 1 inch of rainfall falling on 1 square mile provides 17 million gallons. So we get a lot of millions of gallons falling every year in this county. So the first place that I looked for information was the USGS, what they call the estimated water use in the United States. This is a really interesting database because they've been collecting for every 5 years. They go in and they take a look across the United States, including they go down to the county level and provide information on water use in these various categories there. So this is 2010. Why 2010? Because 2015 is not quite done yet. So as you can see from this, the two big water users here are our public systems as well as our crops, and that we still have a smattering of use in some of these other areas. As a sort of coming from a technical background, I always kind of go, okay, well, you know, they do describe their methods, but how does it compare to some of the local work that we've done here? Because we have done a lot, as I mentioned, in recent years. So I did just a quick look at some of the how this information that they've got in 2010 compares with some of our recent stuff. The coordinated water system plan that was done recently came up with about 20 million gallons for these systems, and you can see it's pretty darn close to the USGS estimate. We have for the, they also said about 5.6 for the smaller single family users. Ag was 54 compared to somewhere just under 45 in the USGS report. Industry was a little bit different, and and I did not have time, and it's really difficult to go into their methods to see exactly what their numbers are, how they derived them. So, but overall, the relationships looked pretty close to what we have done in terms of our more local work on this. So the next thing that I did was to take a look at, okay, what can we say about the history of water use? If we can, on some level, rely on the USGS numbers, let's go back as far as we can. It's back to 1985 because they grouped things similarly back until that point. And so before that, they collected information, but it was much more difficult to tease it out in a way to talk about it today. So what you can see is that for the public water systems, they started up pretty high, dropped down. Ag was the other big ag irrigations, the other one that seems to have a trajectory going up here. And so again, that's 1985 to 2000, about 2015, where the data was available. Pretty even for their estimates for industry and as well as for this domestic, smaller, really small systems, single well users. So one thing to note about when we look at public water systems and why we might have why you see that sort of graph shape there. Public water systems often are not just providing water to single families or home residences. Cities like the city of Bellingham, they also have provided and continue to provide water to industrial customers and business customers. And so that is all embedded in those numbers here. So what might that be a reason for? I don't know, because I wasn't able to look at exactly the explanation from the USGS data. It's probably there if someone had time to look at it. I speculated, having some data from some of the past city reports, that because the city also provided water to Georgia Pacific, and how many people were here when Georgia Pacific was really active on the waterfront? I mean, I went to school and it was right down there, was using water full bore all the time, all year long. So 55 million gallons a day was before basically their peak use. And then the city, in one of their documents said, and this is about when it dropped down a little bit, it's likely that some of that trajectory for that graph is explained possibly by the city of Bellingham and the industrial use that no longer exists for Georgia Pacific. I'm going to talk a little bit more about some possibilities for the ag numbers a little bit later, because I'm going to go into a little more detail about a number of these systems here, these various uses. And the other thing that I did here, because I suspected that, this information is in million gallons a day, so it's use spread out over the course of the entire year. The reality for agriculture irrigation is that we know it doesn't happen over the course of the year. But this is a very crude, I just took the 365 number and spread it over 120 days at an even level. That is not the way it happens in the real world. I know that, but you do get some sense of the numbers are higher in the summer. And again, that's the challenge for us as a community that values our agricultural resources, is how do we help meet those needs at a time when we have the really low stream flows and the low precipitation. So, but we'll talk about that a little bit more. So, quick look at industry, and these numbers, right now, the major industrial provider is the Whatcom County Public Utility District, and these numbers are from their metered readings that from starting in 2009 to 2016. Most of that water, Steve, correct me if I'm wrong, goes to Cherry Point area, most of it. And what I wasn't able to provide in the case of industry is where do we think the industrial demand is going in the future. So if there's questions related to that, there's people in the room that might be able to answer that question. So looking a little bit more closely at what we have for our domestic systems. And I'm going to look at a few things: population changes, where we expect people to be, how they're getting water in terms of those public versus domestic and the sources. And then we'll look a little bit more at the volumes of water that folks are using. And I've got the meter up here, then it illustrates actually that much of the water in terms of our public system quantity of use is actually metered. So even though meters aren't perfect, there's some level of certainty that we can give to some of the numbers, but we don't use metered data for the individual wells or the really small public systems. So you just need to remember that. So here's our population changes, and this actually, I went back to, I guess, 1910, and the Coordinated Water System Plan was required that they have to speculate to 2065 for where people are going to be. And these are largely, the blue represents the expectation that most of the people will be located in city or associated with cities in the urban growth areas versus in the county areas. So as people have commented earlier, we expect a lot more people. We have no reason to think we're not going to continue to get people coming to our community, and the water needs associated with that. So a snapshot in time, breaking that down a little bit, and I just took the year from the information from the Coordinated Water System Plan at the time, and this was recently done, I think it was published 2016, late in 2016. County population of just over 200,000, and most of the people, 80%, get their water from one of those public water systems, and 20% get their water from domestic wells or individual sources. There's a few people that get water from like Lake Whatcom surface water source individually, but by far and away, people are looking at wells here in Whatcom County. And that's so we estimate somewhere around 16,000 wells, individual wells. And so this is a detail that I've just mentioned this. In terms of when you're talking about public water systems, we divide them into Group A's. Group A's are the bigger ones. Group B's are the really small ones. And what you can see is almost all the community and the public systems come from these larger Group A systems. And in reality, they come from a very small handful. Most of our population gets water from this handful of larger public systems. And but you can see, and Dave Olson is going to be talking a little bit more about some of the challenges that these public systems have. We have a lot of public systems here in our community. We have over 400. This is just an example. Since we don't really have a map of where are the individual wells located, we have wells all over the place. And so this just provides an older illustration of wells located in the different aquifers. At some point, it'd be nice to be able to say how many individual wells do we actually have out there and have a map for that. Don't have it at this point. And the other thing is I'm not going to say much more about the individual wells and the future of them right now, because I was not able to find an estimate of how many people we expect to be on individual wells, what the trajectory of that might be in the future. If somebody else knows that, and they might chime in during the question and answer period. So let's take a quick look at the public water systems. Coordinated Water System Plan requires these public systems to identify what they call their service area, and these are the areas that they intend to be able to provide water to anyone within that. They can't always do that for various reasons, but you can see our public water systems are located throughout our county, and I'm going to focus in on some of the big ones here. How am I doing on time, Becky? 5.5 minutes. Okay. So what I want to point out here is that most of the population, half of the people in the county get their water from the city of Bellingham. How many people here are from the city of Bellingham? How many from the rest of the county? So we got a pretty even split here. And they also have the most water use. The water comes from Lake Whatcom. I'm going to give you a quick snapshot of what that looks like. And the other thing to point out here that I think is important in this slide is that, as you can see in the bottom graph here in the cities, that when you look at the cities in terms of the water use, it's 14 million gallons a day. The rest of the public systems are 15 million gallons a day. So the cities and the areas immediately around them are really responsible for much of the water use. This, the blue arrows there, I think are also important to note because cities, a lot of the cities share water. Those blue arrows show connections between a lot of the systems that are out there, and you can see there's a lot of them. It doesn't cover all the smaller systems out there, but many of the larger ones they're sharing water. City of Bellingham shares with Lake Whatcom Water and Sewer District, a couple other water districts. City of Blaine also shares water with Birch Bay. So they're looking at the same source. I'm going to say only one thing about this slide that relates to two topics. One is international border issues, and in particular, this is Sumas. Their water, you saw, Jay talked a little bit about time of travel for groundwater. This is where they think their water is coming from in Canada, and 10, 20 years out, they care about what happens on the other side of the border because it's moving. That's where they're pulling from for their well. So it's part of what we need to think about. Quick snapshot of the City of Bellingham system. You're going to hear a little bit. For those of you not familiar with it, there's going to be a little bit more discussion later about the diversion system. And so I'm going to quick snapshot of that is that City of Bellingham supplements the water directly from the Lake Whatcom watershed, pulling water from the Middle Fork of the Nooksack, and you can see the watershed there, the pipeline, and the diversion system that goes into Mirror Lake and ultimately into Lake Whatcom. So, and then in the future estimates for future public water supplies, you can see that this blue dot represents from the Coordinated Water System Plan where we think the volume of water is going to need to be by 2065. So now we're going to take a quick look at agricultural needs. And we don't have metered data for agriculture, so we have to use surrogates of information. That is typically acres used, the crop type of irrigation system. So here's a quick snapshot of agricultural acreage changes over time. This one goes back to we have there's a really interesting report USDA did looking even back into the 1850s, starting with agriculture and 2 minutes. Jesus. Okay. All right. So anyway, speed it up. So we have fewer acres in agriculture, but more irrigated acres. And the source of water from 85 to 2010, we have heard from the ag community many times, much of it is groundwater, about 80%, some surface water. And here's this breakdown in the crops that have been irrigated. In this case, it was 2014. And so you can see the acres irrigated, which is, and you can, in some cases like corn, there's X number of acres of corn, over 15,000, but they don't irrigate all of them. So that's part of what you got to do with the math for these. And so you combine that with the crop irrigation requirement. We have a lot of berries. Berries have the highest crop irrigation requirement. And you can see what some of the other ones are there. We're getting better at figuring out where all these acres of different things are. Here's an example from a NDVI reflectance data, so we no longer even have to ask people what kind of crops they've got. We can get it from other sources. And so this graph here, what possibly might be accounting for that, I don't know for sure. But when you look at the acres of berries, then you can definitely see that we really started berries, the blueberries and raspberries, stepping up over the years. This does not drop to zero. I didn't know how to get rid of that. So that's operator error there. So, but in any case, there may be other explanations for this upward trajectory for that. And so what is the future of irrigated ag? Well, we think that there's a minimum. The comp plan says we want at least 100,000 acres. We value agricultural production. We need it in this county, but there's no specified amount of water other than a recognition that we really have got to do a better job of trying to make sure that we have water for the land uses that we designate, and agriculture obviously needs water. So I have one more slide, but I'm sure I'm out of time. So she's gonna cut me off. I just wanted to point out that one of the other very early reports that was done in 1953 in response to having a drought that went from September to December said, well, they looked at fisheries, they looked at agriculture, they looked at, municipal needs, and they said, well, what's the future estimate for ag? They said, well, we think in the long run we could probably do it year 2000. We could have a couple 100,000 acres of irrigated ag. And so, but the assumptions were different at that point for that. And they also had ideas of what to do, and this happens to be where they thought we should put the reservoirs at the time, when it was easier to put reservoirs in. But I pointed out because even back then we knew that part of our challenge is not having enough, we don't have enough water, it's holding it and having it in the places that we need it at the times we need it. And the only other thing that I pointed out on here that I think is really interesting is I guess for me, and many of us have probably been working on these issues for a long time, you kind of go, well, let's just fix it and be done with this. I mean, then we can move on to something else, right? Well, we're never going to do that. And this is illustrated, I think, really well by that little that is actually a court case in the early 1900s involving the city of Bellingham. It wasn't the city of Bellingham at the time, but it was a conflict between the city needing to use water for municipal purposes and somebody that had a sawmill. And even back then, this is before the water code, we were having discussions about how do we share the water among competing uses. So we are the latest in an effort to try and address these things and making sure that we do it in a way so that it's not just for now and looking to the future in terms of an institutional framework, I think is really important. How badly did I do? Really bad. All right, so thank you. And I guess we're holding questions. All right, now back to the easier part. So our next speaker here is Triva Ko, and she is with Nooksack Indian Tribe Natural Resources, and she's been there for 18 years, and she is going to talk to us about the fish needs.
Well, thank you, Sue, and thanks for inviting me to give a very brief and quick overview of in-stream flow needs for fish. Well, you heard earlier today about tribal in-stream flow rights that derive from the treaty-protected or treaty reserve fishing rights. Sufficient in-stream flows are required to support a harvestable surplus of salmon, and the priority date of those water rights is time immemorial, which renders them senior water rights. Let's talk about in-stream flow needs for fish. We can all appreciate that flow is the most fundamental component of fish habitat. Without flow, you have no fish habitat. Intuitively, we can understand that as you increase flow in the stream, you increase the volume of fish habitat. Oops, sorry, let me see if I can, is that it? Okay, great. And that's shown in this schematic here, which represents a channel cross-section. More flow in the stream, you have greater water depths and greater potential or volume of potential fish habitat. The same generally is true for area. The more in-stream flow you have in stream, the greater the wetted area. As flows increase, the channel bottom fills up, and in an unconfined channel, that flow spreads out. And so you have greater wetted area of fish habitat. So it sounds simple, right? More flow, more fish habitat. In fact, it's quite a bit more complex than that. In-stream flow fundamentally affects the availability and distribution of depths and velocities through a stream channel. And that has different implications for different species and life stages. This chart shows the relative size of salmon fry. That's what you call salmon when they first emerge from the gravel, and they're very small, relative to an adult coho and adult Chinook. And given these size differences, you can appreciate that there's different depth and velocity preferences. And that's in fact what you see in streams and rivers. Salmon fry will seek out the shallow margins of stream channels where water velocities are slow. They can maintain their position in the channel, in the current, and where they could avoid predators. Adult fish, however, tend to seek out, especially for holding, the deepest parts of the channel. They're large and strong swimmers, and they can sustain high water velocities. So in-stream flow, as a result of these depth and velocity preference differences, in-stream flow needs vary by location. This is a fish distribution map. It shows in black the distribution of Chinook through the Nooksack Basin. Chinook tend to spawn in main stems and larger tributaries. The red lines show coho distribution. They tend to spawn in small and medium-sized tributaries. And so in-stream flow needs are going to vary in those streams depending on what species are present. In-stream flow needs also vary by time of year. This is a periodicity chart. These are the months of the year, January, February through to December. These are life stages. This is a periodicity chart for Chinook in the Nooksack Basin. Spawning generally starts in late summer extending into the fall, depending on the population. You have incubation from eggs in the gravel from late summer into fall and winter. Rearing, you can have rearing fish throughout the year. Chinook can outmigrate its fry when they're really small. They can rear for weeks or months, or they can oversummer and overwinter and go out the following year as yearlings. So you can have Chinook juveniles in the stream channel any time of year. So then in-stream flow needs then can vary by time of year depending on what life stages are present. So while salmon need sufficient flows to complete their life cycle, we tend to focus on the summer months when in-stream flows are most limiting. So this again is this periodicity chart for Chinook. Sorry. Going back and forth to the microphone. And you can see that low in-stream flows in summer affect all life stages of Chinook. Low summer flows also affect steelhead and bull trout, which are also listed under ESA. You have summer steelhead and bull trout moving upstream and holding in the summer. You have winter steelhead that can spawn through June, leaving their incubating eggs susceptible to summer low flows. And then you have both of these species have extended rearing in freshwater. And then for other species, sockeye and pink also move upstream and start to spawn in summer. And sockeye, coho, and cutthroat also have extended freshwater rearing. So how do low flows affect salmon? Well, low flows can create barriers to upstream migration. Flows can go subsurface, or it could be just water depths can be too shallow to really support fish moving upstream. Low flows can affect water quality. Low flows are associated with high temperatures and low dissolved oxygen. That can affect any life stage that's present in the stream, but holding adult salmonids are the most vulnerable. This is a picture on the right of a Chinook female that died before it could spawn. we see a high incidence of pre-spawn mortality, and this is from the South Fork, in the South Fork when the summers are very hot. So spawning salmon have specific depth, velocity, and substrate preferences, and so the amount of flow in the stream can really limit the availability of suitable spawning habitat. This can be really a problem when flows are extremely low and summer spawning fish are confined to the deepest parts of the channel. Those are the areas of the channel that when flows do come up are most susceptible to scour. So that can really be a problem for incubating eggs. So low flows can dewater redds. Redds need sufficient in-stream flow to provide intergravel flow to oxygenate the eggs. If you have flows dropping relative to spawning flows, then it can dewater the redds, or it can lead to unsuitable dissolved oxygen and temperatures for incubation. Juveniles require enough in-stream flow to provide sufficient space to rear, access to cover, and moderate temperatures. Juvenile salmon eat invertebrates that drift from upstream, and so you can imagine that the greater the water velocity, the greater the rate of delivery of that food source. Flow is also really important for connectivity of habitats. When flows drop in the summer, you'll often see juvenile salmon caught in, stranded in isolated pools, and that can be a problem. Lethal temperatures, high predation, and such. Thanks. So low flows limit the amount in productivity and connectivity of rearing habitat. So it's not just about sufficient in-stream flow for fish to complete their life cycle. We also need sufficient in-stream flow to maintain water quality. We need the higher flows that are really important for maintaining the channel, forming habitat, maintaining the riparian zone, and even those large catastrophic floods are really important for valley maintenance, for shaping the floodplain. So, as we know, as we hear, we understand the changing climate will further challenge us. These are kind of typical hydrographs. We have streams throughout our watershed that are rain-dominant systems. That's mostly through the lower watershed, with highest flows in the fall and winter, and really low flows in summer. You have snow-dominated systems, which have that higher peak in kind of late spring into summer due to snow melt and glacier melt. And then you have transitional systems that are kind of, a combination of the two. With climate change, we'll see an increase in those winter flows, especially peak flows, and then reduced summer low flow. That's especially going to be profound for the mixed and snow-dominant systems, but also to a certain extent in rain-dominant systems as well. So that, coupled with increased temperatures and changes in sediment load, is going to further stress our already imperiled fish populations, and as you can appreciate, will further challenge our water issues. So thanks, that's it.
Thank you, Treva. That was right on time. That was really excellent. Our final speaker for this session is going to be Gary Stoika, who's going to talk a little bit more about the importance of science in making our decisions around water resource issues in the watershed. And Gary is the Natural Resource Program Manager for Whatcom County and has been for a number of years, but his history also expands into other parts of our region beyond Whatcom County, doing a lot of this work, and we are happy to have him here this afternoon.
Okay, thank you, Sue. It's great to be here with all these folks that know a lot of stuff about a lot of things for a scientific talk there. My talk is going to be kind of summarizing some of what you just heard. I'm going to try to tell you where we are in terms of gaining knowledge that we need to solve our problems. Some of it's going to be a summary of the 3 talks we just heard, and a little bit of it might be preview for talks this afternoon. I kind of summarized what we need to know in terms of scientifically into a couple of questions here. How much water is there and when? And I should say where also, both for surface water and groundwater. How much water is needed instream. Treva just touched on that for fish and aquatic resources. What is the condition of the habitat? That's something we haven't really talked about yet. And also, what is the quality of the water? We haven't touched on that yet today. And then how much water is needed out of stream? Sue certainly touched on some of that for the different sectors. And then how do we get the water to where we need it? And also looking to the future, we can know a lot about what conditions are now, but what will be the impacts of climate change? And then how do all of these different aspects fit together? So to kind of start in with some of these answers. Again, you've heard many of them today. How much water is there and when? Well, Jay went through quite a bit of the lower Nooksack water budget, mentioned, that really showed us where the surface water is located and when. He also mentioned that the groundwater model that's going on right now, it should be done by the end of 2018, so I put down 2019, is going to tell us a lot about the groundwater model, the groundwater system, where our groundwater is and when that is available for at least the northern 2/3 of Whatcom County. And I just went ahead and threw in there, I know that there are a lot of other studies that have been done, but Dan Isis this afternoon is going to talk about an investigation that they're doing up in the Birch Bay area on a deep aquifer that may present a good source of water that could help solve some of our problems. Just wanted to say a few words about the groundwater model. I know Jay already kind of touched on these, but this graph here, or this figure here, this black line is the groundwater model domain. So you can see Bellingham is down here. It doesn't cover all of the county, but it covers a pretty good chunk of the areas, particularly where groundwater is really kind of a crucial supply. And what you can see here is that this is about a 426 square mile model area. So this is a very large model area as far as models go. Not that it's the biggest ever, but certainly lots of times models are much more smaller area. And this model is coupled with the surface water model, so we certainly want to make sure that we know what the groundwater and the surface water interacting, what that interaction is. But one of the things I wanted to show with this map is that these red dots all over the place are the data points that are being used in the model. They're either providing information about the aquifers, the hydrogeology, or water levels, or hydraulic properties. And what I wanted to show with this a little bit is that you can see that the dots are not evenly distributed. We have lots of dots in some areas and not so many in the others. And what that's going to mean for when the model is done is that we're going to have a lot more information in certain areas. Of course, these densities also, that's where the wells are, so that's showing the areas that are of high use. But what that's going to mean is you're going to have a lot higher confidence in groundwater conditions in the model in areas where you have a high density of data, and a little less confidence in areas where you have a low density of data. The model is going to model this entire area, so you'll be able to plug in scenarios and look at the conditions anywhere, but you're going to have just a much more higher resolution in these areas where you have a higher density of data. So that kind of shows you that moving forward, we may need to supplement this data with additional wells or other monitoring points so that we can fill in the gaps and get a little higher resolution in these other areas. And also the model is currently just going to be looking at current climate conditions, but it certainly is constructed in a way that we can put in future climate scenarios and kind of look at the impacts of climate change to look at how that affects our water supplies. This also shows that we, once the model is done, it won't be done in terms of here, we can walk away from it, but we're going to have a long-term need. Somebody's going to have to maintain this model. We're going to have a need to continue to collect groundwater data so that we know, wow, 5 minutes goes really quickly. So that we need to know, how trends are moving into the future, and also to add additional data as we get it. Some other answer, how much water is needed in stream? I think Triva did a pretty good job of telling us that. So we've done all that modeling, in-stream flow assessments a decade or so ago, and we have that information, so we know what kind of flows give us what kind of habitat for what kind of fish. I also just wanted to point out that in addition to the scientific data, we also, back in the watershed management plan, we adopted an in-stream flow adoption and action plan, which was partially implemented, but in addition to having the scientific data, we also have a process for setting and establishing in-stream flows. So we have a programmatic process already laid out. What is the condition of the habitat? Well, we haven't really touched on that much yet, but you can see here that there's been a whole lot of studies that have been done. So we have a pretty good idea what the condition of the habitat is. And again, like all of these data needs, we have a lot of data here and probably sufficient data to make decisions. We can always use more, but we have a pretty good handle on this. What is the quality of the water? Well, we haven't really touched on that so much right now, or so far, but we do have quite a bit of data. Department of Ecology did a bunch of TMDL studies over the past couple decades. A lot of those were, found that many of our streams have bacterial or dissolved oxygen or temperature problems. There's also been quite a bit of studies that have been done on groundwater nitrates, and as well as I'll point out that there's a program called the Whatcom Clean Water Program, which is collecting a lot of data on fecal coliform in surface water bodies. That's a program that was put together to address fecal coliform contamination of our shellfish beds. So quite a bit of information on water quality. How much water is needed out of stream? Well, Sue kind of touched on really pretty much most of that. The Lower Lickstack Water Budget did an assessment of all that data. Some of that data was refined in the Coordinated Water System Plan that was just completed last year. And also the PUD enlisted RH2 consultants to do an update basically of the agricultural needs assessment in 2016. So we have a pretty good idea of what we need out of stream as well. How do we get the water to where we need it? Well, now we're entering the portion of what we haven't done, what we need to do. That is kind of next on our to-do list, is to come up with a plan. Okay, now we know where the water is and where our water needs are. How can we get the water from where we have a surplus to where we have a deficit? And that's really what we're trying to embark on going forward. And that could be, it could be actually physically moving the water with pipes or something else, or it could be more of a legal or a paper water rights exercise where we're transferring water rights or, doing water banking. What will be the impacts of climate change? Again, we have some information, some climate studies have been done so far. I'm sure that we could supplement that data, but I think we have a sufficient amount of data to at least look at that. The Nooksack Indian Tribe did a study recently, looked particularly at the effects in the South Fork. So we have that information that we can put into our models. How does everything fit together? Well, this is a water supply symposium, and so we're here, to talk primarily about water quantity. But as we've been hearing, and as I pointed out, there's other elements, water quality, habitat, and in-stream flow, and they're all interrelated. And while you can address some of your water quantity, some aspects of your water quantity issues independently, really it's going to be so much more efficient and make a lot more sense to look at all of these elements together, and really look at what's the best mix of quantity, quality, habitat, and in-stream flow that you can come up with to get all the parties and all the needs, let's see, Matt, maybe as it was pointed out earlier today that not everybody gets exactly what they want, but get the right mix of what we need. So we need to look at this in a comprehensive kind of holistic framework. So what is on our to-do list here? Well, develop a water supply plan is one thing, and then the next kind of big effort is going to be developing comprehensive drainage-based management plans. Okay, what does all that mean? Thanks. And that means it's kind of what was outlined in the watershed management plan, but going into an area such as the Bertrand and saying, getting the right people at the table, getting the right data, and sitting down and saying, okay, let's look at the water quality, the quantity, the habitat, and everything, and come up with a plan to meet all the needs for that basin, and then taking that lessons learned and moving on to another sub-basin. Obviously, you can't do every one of those in isolations because you can't want to rob from one basin to meet your needs in your basin. But that's kind of the plan going forward is, hey, let's take a bite-sized chunk, get the right people at the table, and see if we can't solve all of these needs in one area and move on. Of course, the ones we get those plans, they don't do any good if you don't implement them, so we'll need to implement them. And then, of course, monitor effectiveness and long-term monitoring, and then be able to adaptively manage as things change on the ground. The one thing that kind of getting away from the data and the scientific information is how do we move this forward and kind of thinking of it more in a process format. And this is my last slide, so if you're hungry, I'll be done soon. So this diagram here, it probably, I don't know if you can read any of that or much of that, but but that's kind of partially the point of it. What I'm trying to show here is all of the processes that are going on right now in Whatcom County to solve our water needs. You can see there's a lot of them. We've got the watershed planning process that came out of 9082 coming down this way. We've got the agricultural water issues and the WIDs and the tools that they've developed. We've got, salmon recovery process. We've got shellfish. We've got tribal water rights claims and the Lummi settlement process. So we've got all these processes. Some of them we've coordinated. Boy, I really keep hitting the wrong button here. Some of which, yes, some of which have already been coordinated to some degree. But last year in 2016, all of the cities in Whatcom County, the tribes, the PUD, the state, and I'm probably missing somebody off the top of my head, but got together and formed what's called a watershed management board. And the idea is that we want to take all of these processes that are dealing with certain aspects of all these water issues and kind of put it under one coordinating board and kind of look at everything together instead of trying to address these things separately. And so the things in red, so we've got that board formed. The things in red are things we need to do to go forward. The next thing is to develop drainage-based management plans. And I have the state box here. We need significant support from the state, primarily in the form of money, because these things are all expensive, especially when we get to implementing. But also, some of these things are going to take changes to law, and we're going to need the legislature to address them. And then ultimately, we want to get to binding agreements so that everybody feels certainty into what they get. The ag community feels like that they're comfortable in what they got. The tribes feel like they're comfortable in what they got, and the cities feel they're comfortable in what they got. So this is kind of a big picture of where we're trying to take this process. The only other thing I wanted to add is a complete non sequitur, but I just wanted to let people know that it's a pet peeve of us that work at the county that Whatcom County actually does not have a building moratorium for the wells. We actually have an interim ordinance. We had a building moratorium for about 3 weeks. So under the current interim ordinance, people have the option of either showing non-continuity, which, as we've discussed today, is very difficult, or they can mitigate. So those are maybe not options that most people want, but I just wanted to get that in there so that people knew that. And I'm done.
I have to tell you that Becky sent all of us as speakers very firm instructions about practice, keep it simple, and, mixed success, I would say. So I think we have a chance for maybe 1 or 2 questions, if they're brief, before we break for lunch.
This is an Instream flow question. As it relates to Instream flow and the term time immemorial, Do the Nooksacks and the Lemmies consider the in-stream flow a federal water right? And if so, does that mean the reservation itself has to be a federal trust reservation as opposed to a public domain reservation?
So the in-stream flows that are established in the WAC, those are, that's state, state law. You heard earlier that tribes have rights to sufficient water to support their reservations on reservation use, but also and those rights have a priority date of when the reservations were established, and then and they are federal reservations. But the in-stream flow rights, because tribes have been fishing since time immemorial, they reserve those rights to continue fishing in entering into treaties with the U.S. So, and there needs to be sufficient flow to support a harvestable surplus. Those water rights, tribal in-stream flow water rights, are have a priority date of time immemorial. Does that answer your question?
Well, it was the land status of the reservation. Do you consider the reservation needing to be a federal trust reservation as opposed to a public domain reservation to have those rights?
Doug, do you want to come to a microphone?
Yeah.
And I'll step aside so you can come up here and answer that.
The state in-stream flow rule is not a reservation. It doesn't guarantee a flow. What it does is conditions or regulates new water rights that are junior to the in-stream flow in 1985, so that you can't further reduce or limit or impair the in-stream flows that exist. So it's like a water right. It's not a reservation.
Earlier, we heard from Jay and heard about the successes in the Yakima Basin with the egg lobby and tribes. And I'm just wondering if this flow chart that we're looking at up here maybe takes into account some of the successes that they realized and how they implemented their success.
I'm not that familiar with exactly what process was used in the Yakima, but to the extent that we're trying to bring everybody to the table and kind of take all of these processes that have kind of developed over the years for very specific purposes and put them into one process where everybody can kind of be at the table to discuss all these things, then if that's what Yakima did, which sounds like what happened, then I guess we're doing that in the spirit of that.